Okay, so good afternoon, everyone. So firstly, I would like to thank the organizers for giving me this opportunity to present our work here, although this is not a very good occasion. In my lifetime, I have met Rohini ma'am at Suzy TIFR in a conference, and we didn't get to talk too much, but luckily last year on a visit to IOP, I got involved in a project with Manimala, Genevieve et al., and I got to really work a bit with her in person, and her energy, enthusiasm, and decisiveness particularly struck me. And it's just, I think it was very inspirational and also a very sudden opportunity for me to interact with someone so great. So I will be mainly not talking about the work we did, which Manimaladi already covered, but I will be talking about something we have been working on mainly in the context of, again, a Higgs dark matter connection. And this is a work we did with my collaborators here, and I will talk mainly about some ongoing work also which we are following up currently. So of course this audience does not need to know why we need new physics. I just want to reiterate that there is something called dark matter, which is about 5 times the amount of ordinary matter that we see around us, and we are unable to yet understand what it is. So it's imperative that we focus on dark matter motivated studies, and in this direction I will be talking about a multi-Higgs model, namely the 2 Higgs doublet model, which is extended with a complex scalar singlet, and we will see that a component of the singlet can act as the dark matter. And such scalar singlets are not novel. They have been considered before as well. So these are singlets under the standard model gauge group, and they can be potential dark matter candidates. And in earlier works of Barger et al. And others, people have looked at the Higgs, the 125 GeV Higgs, which has been discovered at the LHC in 2012 as a possible portal to the dark sector. However, new data from direct detection searches constrain the Higgs to dark matter coupling quite stringently. So in case there are additional portals to dark matter present, one can actually alleviate these constraints, and extended Higgs models actually provide extra Higgses which can do the job for us. So of course in the 2 Higgs doublet model, there are special cases which can provide a dark matter candidate, like the inert doublet model, which people have extensively studied over the past years. So I will be mainly focusing on singlet extensions of 2 Higgs doublet model, and there have been previous works in this direction with real singlet extensions, popularly known as the N2HDM models, which also provides extra CP even, which also provides either extra Higgses, or the singlet can act as a dark matter. So there are various different works in this direction. And there are also studies where the singlets can provide contributions to baryogenesis and so on. And in the recent years, there have also been extensions with complex scalar singlets, which can also address dark matter, baryogenesis, inflation, and strong CP problem, and so on. So these kind of complex scalar extensions do have a lot of motivations beside dark matter and collider physics. So we will talk mainly about the situation where the complex scalar singlet participates in dark matter and can also provide an extra Higgs, which can address some excesses that are being observed at the LHC. So there are some recent excesses observed in some specific modes, like the H2 gamma gamma around the 95 GeV window, which CMS has seen in H2 gamma gamma as well as in H2 tau tau subsequently. And although these are of around 2.9 sigma excesses only, they are not yet 3 sigma or 5 sigma. They still need more data to affirm these. But the fact that they are all around the same mass window has caused tremendous excitement. And one can also look back previously to the LEP studies, where people also found a small excess around 2.3 sigma in the H2BB bar mode around this 95 to 98 GeV window. So the concurrence of all of these measurements along the same mass window roughly is a very exciting feature. And while this model can of course have parameters where one does not fit this kind of an excess, you can always try to see if one can accommodate this thing in such models. So we will mainly focus on the type 2 Higgs doublet model, where these phi1 and phi2 are the 2 Higgs doublets, and the S is a complex scalar singlet, which is stabilized under a new Z2 prime symmetry. And we assume that it's only the real part of the complex scalar which obtains the wave Vs and hence mixes with the Higgs doublets. So this is the standard 2 Higgs doublet model Lagrangian, where we are focusing mainly on the CP conserving scenario. And this Vs is the singlet potential that we are adding, and where the important terms are the ones in red, which mainly include the couplings of the singlet to the Higgs doublets phi1 and phi2, and these couplings are the portal couplings, lambda 1 prime, 2 prime, which later on will play an important role when one considers the constraints from direct detection. And after electroweak symmetry breaking, as I was mentioning, there are extra Higgses. So you have 2 CP even Higgs, 1 pseudoscalar, 1 charged Higgs, a pseudoscalar dark matter candidate, and also an extra CP even Higgs. And for this work, we specifically set the lightest one to be 95 GeV and the second one to be 125. And we work in this particular mass spaces scenario. This is mainly to help try to understand the 95 GeV excess better. So we mainly parameterize the coupling CH1BB and CH1TT, where H1 is the 95 GeV Higgs. And we choose these kind of couplings as basis parameters because we are inspired by this previous reference by Heinemeyer et al., where they also tried to look at a similar Higgs sector, which is 3 by 3 in 2HDMS, and they tried to fit this BB bar and gamma gamma excess there. So, and this I would not encourage you to look in detail, but just to point out that in the dark sector, the relevant couplings that are necessary are the trilinear couplings of the Higgs to dark matter, and the quartic couplings of Higgs-Higgs DMDM. And more importantly, these factors of delta prime 1, 4 and delta prime 2, 5 enter. And later on, we'll see that these delta primes are functions of the portal couplings that I was mentioning here. And they get severely constrained. And these are some of the diagrams, the Feynman diagrams, which enter the computation for the relic density and the direct detection. So I will just summarize some of the main results. So on this slide, we basically look at the plane of mu lep versus mu CMS, where mu lep and mu CMS are the signal strengths in the CMS gamma gamma mode and the BB bar mode in lep. And we try to see the impact of all the constraints, both theoretical constraints including the boundedness from below, from Higgs bounds, from direct detection searches like LZ, and from Fermi-Lat. And we see that we have a large parameter space which still survives and is consistent with the 95 GeV excess strengths. And as I was mentioning, in this case, the two main couplings which play a role in explaining these excesses are the CH1BB and CH1TT, and they are sort of varied in this range, which are compatible with this observation. And there are some salient features that we observe, that mainly because H1 and H2 in this case are very close by, there are some cancellations which we see here along the blue lines, which are particularly useful to fit the LZ constraint, which is very stringent. And there are also some dominant dark matter annihilation channels, mainly into the di-Higgs mode. So the Fermi-Lat constraints were also not very stringent in this particular case. However, the LZ constraints are very stringent, as I was mentioning, and these are the two portal coupling combinations that I was pointing out before. So delta 1, 4 is defined as this combination, where the 1, 4 basically it couples to phi 1, and delta 2, 5 prime basically are the portal couplings associated with phi 2 and the singlet coupling. And we see that it's only this green strip that remains after all experimental constraints and theoretical constraints are taken into account. Especially the LZ constraint, which are these yellow lines that you see all over this plot. They are very, very constraining for this particular model, and we could only constrain delta 2, 5 prime around 0.25. Whereas delta 1, 4 prime is relatively free because there is a dependence on cos beta and sin beta, which turns out to be important at large time beta, which I will not go into in much detail. And among other relevant features, I'll just flash some of the important planes that we observed and the important parameters which were constrained. So in this plot on the right, there is this mass parameter ms prime square and the dark matter mass on the x-axis. And as with any BSM scenario with such extra Higgses, we observe the dips at around the a standard model like Higgs mass over 2 and the heavy Higgs mass over 2. So for this case, we are showing these plots for a 900 GeV benchmark point for the heavy Higgs. So we see these kind of dips around 450 GeV and 60 GeV, where the SM Higgs and the heavy Higgs regions open up. And if you see on the right, these are the plots where the z-axis has the sigma, the spin-independent cross-section with proton and neutron, and almost all of the parameter space is very, very constrained, except for a very narrow strip here. And also for Fermi-lat, we do have some stringent constraints also in the channels from WW. And all in all, if you look at the summary plot, it seems that only a very narrow strip of data remains allowed in this plane. However, I would like to point out that at this stage we were doing a very conservative study, so we were not doing any kind of rescaling for underabundant dark matter, which we are doing now in the follow-up work. And we see that if one correctly accounts for underabundant dark matter, one has to scale the direct detection cross sections accordingly, and one can really open up a large amount of the parameter space. And what is interesting is that we do find a lot of benchmarks in these kind of regions where the relic density, even though it's underabundant, it has a very large invisible branching fraction which facilitates collider searches. So coming to collider phenomenology, I'm just showing you a single benchmark pointed out here as a red star, just to show what kind of modes are possible here. So while in 2 Higgs doublet model, you of course have the standard SM-like modes into BB bar. There are also additional modes into di-Higgs, as well as these kind of dark matter pair channels open up. And for this study particularly, we have like a 25% branching into the invisible mode. And we had looked at high luminosity LHC for this search, but from gluon fusion and VBF, we found that it does not have very good significance. One can go at most up to 3 sigma or 2.6 sigma from gluon fusion for this benchmarks. And of course, if one reduces the mass, it can get better. So that's something we are looking at, and even alternate channels like VBH. But we wanted to look at what lepton colliders could provide us. So we compared a generic E plus E minus machine and a proposed muon collider that there is a lot of excitement about in the community now. And on the right, on the left hand side, you see a plot where we have the monophoton plus missing energy cross section. Cross section on the y-axis, and on the x-axis we have the root S, which is the center of mass energy. So the lines in red are the cross sections for the muon collider, the mu plus mu minus going to a single photon and 2 dark matter candidates, and the one in green is the one from E plus E minus colliders, and these are all unpolarized cross section at this stage. So here we see that because of the Yukawa coupling of the muon being much larger than the electron, we do see a huge enhancement in the cross section, and this actually is very useful because one can try to look for these kind of modes at a muon collider much more efficiently than at electron colliders at higher root S energies. And similarly for the mono Z plus missing energy channel, we observe similar enhancement. So keeping this in mind, we now try to find some benchmarks from our study, and which have a variety of heavy Higgs masses ranging from 650 GeV to 900 and even 3 TeV, so that we are closer to the click target root S value, and a variety of dark matter masses varying from light in the sense of 55 GeV. It's not as light as MEV or EV, but we are still in the GeV range. And so yeah, 55 GeV to about 1 TeV. And from the benchmarks that we have chosen, we see that there are scenarios where one can have a good thermal relic abundance as well as underabundant scenarios. And in some of these underabundant scenarios, one actually has a very large branching fraction of the heaviest Higgs H3 to chi-chi, as high as 69%. So one expects that these could be good benchmark scenarios for colliders to look at, and we mainly look at now the mono photon and the mono Z plus missing energy searches, as I was pointing out. And the dominant backgrounds are the nu gamma and nu Z respectively for these two channels. And here I present the two extreme benchmarks, namely the BP55, which is the lighter one here, which one can probe actually best at the 250 GeV ILC like E plus E minus collider with around close to 5 sigma or even 7 sigma if one goes to a higher luminosity of 3 Autobahn inverse. And at a muon collider of 1 TeV also one can probe this benchmark with about 5 sigma excess if one runs it up to 10 Autobahn inverse. However, at 3 TeV the situation is not so good for this benchmark, and BP2900 as expected is only sensitive to the 3 TeV case, and this is also not a very good channel to probe this particular benchmark. However, these two channels are good for lighter benchmarks like the ones we see here, where one can reach good significances even at ILC and at higher energy muon colliders. And we mainly do this analysis using certain variables like the missing mass and the photon energies. So one can actually have significances up to 5 sigma at 10 Autobahn inverse for these kind of benchmarks. As well as for mono Z plus missing energy, one can use the missing mass variable to sort of exclude background, and here also there is a possibility of having a reasonably large excess at a 1 TeV muon collider. Of course, we know that there are muon collider studies being proposed from 3 TeV onwards, so that is something we are currently working on, and whether we can improve the significance for the BP2900 benchmarks by considering alternate signal channels like BBH or TTH, which can be more competitive than the two that we have studied here. So this is still underway. So yeah, I would like to summarize that we mainly have looked at this type 2 Higgs doublet model extended with a complex scalar in the context of accommodating a 95 GeV excess dark matter, as well as probing some signals at future colliders. And although high luminosity LHC has some sensitivity for this kind of a scenario up to 3 sigma or 2.6 sigma from the GGF channel, one has to look at other channels like BBH, which we are also currently looking at, because the BBH channel actually does have some enhancements in these kind of type 2 Higgs doublet models. And of course, there are also potentially exciting signatures which may be possible at lepton colliders because of the enhanced Yukawa coupling of the muon, as well as the cleaner environment of these lepton colliders. So all of these colliders are very important to probe these kind of models, and hopefully we will be out with the results for the full collider simulation of all of these channels soon. And before ending, I would just like to point out that this was the work which I got a chance to participate in the later stages, and there were some collider signals that were looked at mainly from the decays of these extra Higgses and extra charged Higgses, which were discussed in an earlier talk today, which can lead to multiple photons in the final state. And these kind of extra singlet extended models can also have signal channels at high luminosity LHC, which would be very interesting to look at. So yeah, thank you very much.